So now let's take a problem which is based on availability and irreversibility. So first I am writing the problem here and then we will solve the problem. Air expands through a turbine from 500 kilopascal to 500 kilopascal 520 degrees centigrade to 100 kilopascal 300 degrees centigrade. During expansion 10 kilojoule per kg of heat is lost to the surrounding which is at 98 kilopascal 20 degrees centigrade. Neglecting the kinetic energy and potential energy changes, determine per kg of air determine per kg of air A. The decrease in availability. The decrease in availability. B. The maximum work. C. The irreversibility. For air, take Cp equals to 1.005 kilojoule per kg Kelvin. H equals to Cpt, where Cp is constant. So now let's solve the problem. So I am writing solution here. We know by first law of thermodynamics, TdS equals to del H minus VdP. So the entropy change of the air in expansion process. So the entropy change of air in the expansion process is del S, that is from 1 to 2 equals to 1 to 2 m Cp del T by T minus 1 to 2 mR del P by P. So now we can write by integration S2 minus S1 equals to mCp ln T2 by T1 minus mR ln P2 by P1. So now for 1 kg of air, because you have to determine all these things for 1 kg of air, that is for per unit mass, S2 minus S1 will be Cp ln T2 by T1 minus R ln P2 by P1. So now we are having change in availability formula. So change in availability change in availability, availability, psi1 minus psi2 equals to P1 minus B2, that is H1 minus T0 S1 minus H2 minus T0 S2. That is B is nothing but the Kinon functions we have already discussed in theory. So now again we can simplify it. H1 minus H2 minus of T0 S1 minus S2. So now H1 minus S2 means for enthalpy we can take CPT. So here I can write Cp T1 minus T2 minus T0. In place of S1 minus S2 I can write, for S1 minus S2 I can write R ln P2 by P1 minus of Cp ln T2 by T1. So now we have to put the values of Cp, T1, T2, T0, P2, P1 for this equation. So Cp is 1.005, T1 is 520, T2 that is 300 minus T0 that is 293, R for air that is 0.287, ln P2 that is 1, P1 that is 5 minus again Cp 1.005 here, and ln T2 is 573 divided by T1 that is 793. So now if we put this value and calculate, then change in availability psi1 minus psi2 will be 1.005 into 220 minus 293.3267 minus 0.4619. This value we got from the previous equation. So now we can write 2 to 1.1 plus 39.6. So we are having 260.7 kilojoule per kg. So the maximum work will be change in availability. So I can write maximum work will be W max will be change in availability. So it will be psi1 minus psi2. So 260.7 kilojoule per kg. So the maximum work will come 260.7 kilojoule per kg. Now with the help of steady flow energy equation, I can write the equation for turbine. So I will write from steady flow energy equation, I can write Q plus H1 equals to W plus H2. So W will be H1 minus H2 plus Q. So now in place of H1 I can write Cp T1 minus T2 plus Q. So W equals to Cp we know that is 1.005, T1 520, T2 is 300 minus 10. So W will be 211.1 kilojoule per kg. So that is the actual work. So now we can easily find out irreversibility. So for irreversibility, that is I can write I equals to W max minus W. So W max is 260.7 kilojoule per kg minus the actual work done, that is 211.1 kilojoule per kg. So now irreversibility will come 49.6 kilojoule per kg. So the irreversibility we can calculate by this way. It is coming 49.6 kilojoule per kg. So there is a one alternate method is also. We know the irreversibility is product of ambient temperature and change in entropy for universe. So alternate method I will describe alternate method. In this alternate method we will apply the formula I equals to T naught, this for universe, so del S system plus del S surrounding, del S surrounding. So now for I equals to T naught, that is 293 ambient temperature, del S system, or I can write 1.005 into ln 573 by 793 minus of 0.287 ln 1 by 5 plus 10 by 293, 10 by 290. So if I calculate this thing, it will come in 293 into 0.1352 plus 10. So now if I doing calculating this thing, it is coming 49.6 kilojoule per kg. So by this way also I can easily find out the irreversibility. So this is a very good example which is showing the change in availability, maximum work and irreversibility we can calculate easily with the help of simple formulas. And another problem, so I am writing the problem here. Neglecting changes in kinetic, neglecting changes in kinetic energy and potential energy for for unit mass, the availability of unit mass, the availability of a known flow process, of a known flow process becomes A equals to phi minus phi 0, where phi is availability function of the A option, that is open system, B option it's closed system, C option isolated system, and D option it's steady flow process, steady flow process. So as we already discussed in the theory part, this kind of thing for a known flow process, the phi minus phi 1, that is the availability function, and it is applicable for closed system. So the correct answer for this problem is B, that is closed system. So the B will be the correct option. Now I am considering the second problem. I am writing the problem here. Availability function for a closed system, availability function for a closed system is expressed as is expressed as A phi equals to u plus p naught v minus t naught s, b phi equals to del u plus p naught v plus t naught ts, c option phi equals to del u plus p naught v minus t naught ls, and D option phi equals to u plus p naught v minus t naught s. So as uh, as our previous discussion, which is based on a theoretical concept of availability and irreversibility, we know the availability function for a closed system will be u plus p naught v minus t naught s. So the correct answer for this problem is A, phi equals to u plus p naught v minus t naught s. Now let's take another problem. So I am writing the problem here. Ratio of specific heat ratio of specific heat for an ideal gas for an ideal gas is is given by A option 1 divided by 1 minus R by Cp, B option 1 by 1 minus Cp by R, C option 1 by 1 plus Cp by R, D option 1 by 1 plus R by Cp. So now we have to just go for a small calculation and then we can easily find out. We are interested in ratio of specific heat. So we know Cp minus Cv equals to R. So now if we divide the LHS and RHS by Cp, I can write Cp by Cp minus Cv by Cp equals to R by Cp. So that is 1 minus Cv by Cp equals to R by Cp. Now we know Cp by Cv equals to gamma. That is the ratio of specific heat. So 1 minus 1 by gamma equals to R by Cp. So 1 minus R by Cp equals to 1 by gamma. So now if we reciprocate, so 1 upon 1 minus R by Cp will be the ratio of specific heat. So the correct answer is gamma, that is ratio of specific heat, will be 1 upon 1 minus R by Cp. So the correct answer in this problem will be A. I am writing another problem. I am writing the problem here. Choose the correct expression. Choose the correct expression for Joule Kelvin, for the Joule Kelvin coefficient A mu j equals to 1 by Cv T del V by del T at constant pressure minus V. The B option, that is mu j 1 by Cp T del V by del T by P minus V. C option, mu j equals to 1 by Cp T del V by del T at constant volume minus P. And D option, mu j equals to 1 by Cv T del V by del T at constant volume minus P. So now I would like to discuss about Joule Kelvin effect, and then we will see how we can get the correct expression. So now I am giving the solution for this problem. So I will talk about first Joule Kelvin effect. So here I will first describe the Joule Kelvin coefficient. So the Joule Kelvin coefficient, which is denoted by mu j. So mu j is nothing but del T by del P at constant enthalpy. So we can define the Joule Kelvin coefficient is del T by del P at constant enthalpy. So here I am drawing the curve on TS diagram, that is TP diagram, temperature, pressure diagram. Here I am having the curves which is having constant enthalpy. So I am having these curves which are having the constant enthalpy. So in that process, if I join the peak, I will be having this kind of curve which is joining the peak here. These all curves are constant enthalpy curves. All curves are constant enthalpy curve. Constant enthalpy. So here, if we join the top points of all these curves, we will get an inversion curve. That is called maximum inversion temperature. Here we are having maximum inversion temperature. So here if you see this dotted line, so from origin to dotted line we are having positive mu j, and outside the dotted line we are having negative mu j. So this origin to this dotted line, it is cooling region. Cooling, and here it is heating. So remember one thing, for positive Joule Kelvin coefficient there is a cooling, for negative Joule Kelvin coefficient there is a heating. So now come to our problem. By first law of thermodynamics, I can write del H equals to TdS plus VdP. So TdS I can write by the second TdS equation, that is Cp delta T minus T del V by del T at constant pressure into Tp. That is second TdS equation. That is second TdS equation. For second TdS equation, we can write TdS equals to Cp delta T minus T del V by del T at constant pressure into dP. Now if we put TdS value in the first equation, I will get del H equals to Cp delta T minus of Cp delta T minus of T minus of T del V del T at constant pressure minus V dP. So from first two equation I can write del H equals to Cp dt minus T del V by del T at constant pressure minus V dP. For constant enthalpy process, del H will be 0. For constant enthalpy process, the del H will be 0. For constant enthalpy process, del H will be 0. So I can write for constant enthalpy process, enthalpy process, del H will be 0. So now I will get 0 equals to Cp delta T minus of T del V by del T at constant pressure minus V del V. So now we know the mu J is nothing but del T by del P at constant enthalpy. So now if I go del T by del P at constant enthalpy, so here if I rearrange this equation, I will get Cp delta T equals to T del V del T constant pressure P minus Cv dP. So now at constant enthalpy I can write del T by del P at constant enthalpy will be 1 by Cp T del V by del T at constant pressure minus T. So now see this thing, this is nothing but mu J, so I can write mu J. So mu J will be 1 by Cp into T del V by del T at constant pressure minus V. So correct answer is P. Let's take another problem. So I am writing the problem here. So now let's take another problem. So I am just writing the problem here first and then we will solve it. A steel block of mass 5 kg is at 500 Kelvin. The ambient temperature is 300 Kelvin. The specific heat of steel the specific heat of steel is 0.5 kilojoule per kg Kelvin. Calculate the available energy of the block. Calculate the available energy of the block. So now let's solve the problem. Here the steel block of mass 5 kg at 500 Kelvin is given. The ambient temperature is given 300 Kelvin and the specific heat of steel is 0.5 kilojoule per kg Kelvin is given. Now we have to find out the available energy of the block. So we know Q1 is equals to available energy plus unavailable energy. So now for Q1 we can calculate with the help of formula mc delta T. So Q1 equals to mc delta T is T2 minus T1. So here it is mentioning like our T2, that is the steel block of mass is at 500 Kelvin, means it is T1 and T2 is 300 Kelvin. So I will write first here, that is T1 is 500 Kelvin, T2 is 300 Kelvin and C it is 0.5 kilojoule per kg Kelvin. So now first calculate Q1. Q1 will be M, that is 5 kg. M I will mention, that is 5 kg. 5 into C is 0.5. T2 that is 300 minus 500. So Q1 will be 5 into 0.5 into 200 it will be 500 kilojoule. So it will be 500 kilojoule. Negative. So, but here in that equation we are interested only in magnitude. So we will take 500 kilojoule. So unavailable energy, we are having the formula T0 plus 2 into del S. For T naught, that is ambient, it is given 300 Kelvin. And for S naught, or for del S, we can calculate with the help of this formula MC ln T2 by T1. So here mass is 5 kg, C is 0.5 ln T2 here is 300, T1 here is 500. So now if we calculate this thing, it is 300 divided by 500. If we take log of it into zero point 0.5 into zero point 0.5, zero point 0.5 into 5, it will come 1.28. So it will come minus 1.28. So the UE, that is unavailable energy, that is T naught del S, it will come 300 into 1.28. So 300 into 1.28, it will come 383.1. That is 383.1 kilojoule per kg. Kilojoule. It will be in kilojoule. So now we know Q1 equals to AE plus UE. So for AE, I can write Q1 minus UE, unavailable energy. Q1, in that equation we have to consider only magnitude, that is 500, minus 383.1. So it will come around 116.9. So the correct answer will be 116.9 kilojoule. So by this way we can easily calculate the available energy.